Hi, the subject of this video is to write C++ code to convert Midi events data to audio data using a VST plugin. If you haven't seen part 1 of this series of videos, I suggest you go back and watch it. The material in each video builds on the things that have been covered before. Pardon my raspy voice today, I've got a cold and a sore throat. I hope it's not too annoying. Last time we wrote code to load a plugin, prepare it for processing, and we obtained and displayed some of the particulars of the plugin. I also talked about the callback function, which the plugin uses to notify the host, also known as audio master, about something and to get certain bits of information which might or might not be essential for the plugin's proper functioning. As far as the main function is concerned, this is the new line of code here. The implementation of Play Midi tune is here, and we will spend most of our time walking through the source code, but not until I discuss some preliminaries. As I said before, the input data comes from a Midi file. Our program needs to know how to read and pass that file. There are 3 types of Midi files, and for testing I'll create and use type 0 Midi files. A type 0 Midi file consists of a header and a single track. The header itself consists of the literal string mthd, followed by the length of the header, which is always 6, and then in our case the format is 0, as this is a type 0 Midi file, and the number of tracks is 1. The green number under the individual items denotes the length of each item in bytes. The start of the track is marked with the literal string mtrk, then the length of the track starting from the byte that follows the length field, and it also includes the end of file marker. The rest of the track is made up of events. There are 3 types of events, but we will only concern ourselves with Midi events. To keep things simple, meta events and sysx events will be excluded from the test files. Now take a look at the timestamp. It's called variable time because it can consist of 1 to 4 bytes and has an unusual format. And to explain how it works, let me bring up this calculator. The largest timestamp value that can be stored in 1 byte is hexadecimal 7f. It's because the rightmost bit must be 0. So the next number up is not hexadecimal 80 as you might expect, because that would mean that the rightmost bit becomes 1, but instead it is this number. It's as if the rightmost bit in the first byte was shifted left by 1 place. This 1 here signifies that this byte is not the last one in the row. The last one has its high order bit set to 0. So as the program is reading the timestamp, if it sees a byte whose value is hexadecimal 80 or larger, then it knows that additional timestamp bytes will follow. When it finds one whose value is less than hexadecimal 80, then it knows that that's the last one, or the only one. The largest number possible in 2 bytes according to this system is this. If we want an even larger timestamp, then we need to add another byte and another byte, up to this very large number. This is a simple Midi file with only 2 musical notes in it. The first note starts here and ends here, and the second starts here and ends here. Note start and note end are separate events, and both are preceded by a timestamp. The first timestamp is here, and it consists of 2 bytes. As you can see, it is in the variable length format. The binary representation of that number is this. And notice that the most significant bit of the high-order byte is 1, and the most significant bit of the low-order byte is 0. Just for completeness, the header goes from here to here. These 4 bytes are the header length, always equal to 6. The next 2 bytes are the format, followed by the number of tracks, which is 1. And lastly, the time division. Hexadecimal 3C0 equals decimal 960, and it encodes the number of ticks per quarter note. I will discuss what that really means, so don't worry about it now. The track begins here, this is the length of the track, and then here is the first timestamp. The file ends with the end of file marker. Back in the simple VST host program, I created a class called Midi tune, and in that class there is a method that reads a Midi file. And stores that event data in a vector. Look at this function here. This is when the variable length timestamp is unpacked and converted into a normal number. The actual data items stored in the vector are of type VST Midi event. VST Midi event is a struct defined in the Steinberg VST API. When we talk about Midi events data as our input and generate sound data, that data is a digital representation of sound. What does that mean? The analog sound or audio signal in digital form is just a series of samples taken at discrete time intervals. The per second frequency of those intervals is called sample rate. Higher sample rates provide a better fit to the analog signal. In my program, I will use 44.1 kHz, which is more than adequate. Another consideration is the encoding of the amplitude of the sound. In 16-bit samples, that is in 2 bytes, we can store a large enough dynamic range. It translates to about 96 decibels. In relation to audio, we also talk about channels. In stereo audio, we have a left and right channel. Each channel is sampled separately, and here is a term which is sometimes used incorrectly. A frame is the collection of samples in all the channels at a point in time. So for stereo, a frame consists of 2 samples. Digital audio data is passed around in the computer in chunks called buffers rather than as individual samples or frames, for obvious reasons. Choosing an optimal buffer size is important. Larger buffers take longer to fill with data and could introduce unacceptable latency, whereas with smaller buffers the CPU is made to work harder and possibly less efficiently. In my program, when you see block size, that's analogous with buffer size, and its value is 512. That is, it can hold 512 frames. Now I'm going to try to explain how the processing of Midi events data and its conversion to audio output with a plugin is done. They say a picture is worth 1,000 words, so I created this diagram. On the left here, you see the Midi events that are coming in from the Midi file. A note on event followed by a note off event, and then another note on event, and a note off event. And these are the variable time values. The green line is a timeline. Even though we are working with Midi events, The procedure is similar to sampling analog audio input. We need a timekeeper, a clock, that is ticking at constant time intervals and sampling the input. The sequence of events is as follows. The first note on Midi event is read, but it is in the future as the time value is larger than 0. So as the audio clock is ticking along, the plugin is generating silence. The output from the plugin is just zeros. Then, at a later time, when the waiting time for this first event has elapsed, then this event is processed by the plugin, and from then on we get sound. Then the next Midi event is read, which would turn off the sound because it's a note off message, but again it's in the future, so it only gets processed by the plugin when its timestamp has expired. Here. Don't worry if you don't understand everything on this diagram yet. It will make a lot more sense later, after we covered a few other things. For instance, you may wonder, what is the relationship between the time that passes between two successive ticks of the audio clock and the time values attached to each Midi event? In order to see that, we need to familiarize ourselves with some terms and their meanings. As I said before, samples are processed not one by one, but in buffer-size chunks, and I use the word block size for the buffer size just because I read it somewhere and it stuck with me. In my program, the block size is 512, meaning that there are 512 sample frames in each block. At the same time, one tick of the audio clock, expressed in sample frames, is also 512. So block size equals sample frames per tick equals 512. Remember that in the Midi file, we met a value called division, or time division, and it represented the number of ticks per quarter note. Ticks is an elusive concept, but think of it as hash marks on a timeline. Equally spaced, but the distance between them can vary. For instance, the ticks can occur more or less frequently depending on the tempo. That leads us to this formula. Ticks per second equals time division times tempo over 60. A typical value for tempo is 120. We can now also calculate the number of sample frames per tick based on the sample rate. Sample frames per tick equals sample rate over ticks per second. Remember, when I talked about sample rate, I said the sample rate of 44.1 kHz was significantly large to reproduce the frequency spectrum of human hearing. In a Midi event, the time value is expressed in ticks, and it is equal to time in seconds times ticks per second. In my program, I named this variable note length, and in retrospect, that was a bad choice, because in reality it is the delta time between two events, but I'm not going to change it now. I think you can see it now that there are two time values at play here. On the one hand, we have the audio clock ticking along at a constant rate, and what I call the Midi clock, which marks the passage of time between Midi events. The way I implemented the Midi clock is that it accumulates these delta times as they occur, and I express it like this. On the other hand, the audio clock is advancing in block size increments, so the current audio clock time is the sum of all previous advances. And now a crucial question. When is a Midi event ready for processing? Well, it is when the audio clock catches up with the Midi clock, expressed like this. I wonder if my explanation was clear enough. In the comments below, please tell me if you are confused about something. It certainly took me quite some time to figure all this out. Okay, now how does everything we've covered so far look like in practice? Here is some pseudo code. I've spoken long enough, so I'm not going to read out what's on the screen. You can stop the video and ponder over it. Since this video is getting too long already, I'll just show you some of the source code I've written. This is the implementation of the pseudo code. Of course, there are some additional tasks being performed here as well, like allocating memory for the buffer and whatnot. Please note, I'm not coding in modern C++, partly because the Steinberg API is not written like that either, and partly because the code examples I learned from were old-fashioned C and C++. Sometime in the future I might convert this to modern C++, but for the time being that's not my priority. Here I combined the audio clock and the MIDI clock in one class. And here is the function to test if it is time to process a MIDI event. Further up, this is where the MIDI clock is advanced. And this is where the audio clock is advanced. Here, the first MIDI note event is read, and also the MIDI clock is advanced by the length of time stored in the variable time field of that event. If the time value is 0, then the event is processed straight away. So we hear that musical note played immediately. And here is our loop. There is the test to see if it is time to process the MIDI event. If it is, then it is added to a list, and then the next event is read. We do that repeatedly and build a list if more than one event occurs at the same time, for instance when a chord is played. And here the process MIDI event function is called in the plugin. That's my plugin object, not the real plugin. The code to the real plugin is here. And if you watched the previous video, then this should look familiar. At each and every tick of the audio clock, the generate output function is executed. Again, first in my plugin object, and then in the real plugin object. The input buffer is not used here. The input buffer is for plugins that take audio data as their input and do something with it. A plugin like that would be an equalizer, or one that applies distortion or some other effect to the sound. The output buffer is where the generated sound comes back. As you can see, they are floats, one set of values for each channel, and those values are in the range from -1 to +1, and 0 means silence. Before the end of the loop, the audio clock is advanced. Now I will run this program. You probably noticed that I've got print statements here and there to trace the execution of the program, and that's what we are going to see on the console. The MIDI test file is the one you've seen before, and I'm using the VST synth plugin from last time. This is where it all starts. Initially we get zeros, that is silence, as could be expected. Each iteration is a tick of the audio clock. The first MIDI event gets processed here, and then we start getting sound data. See here how the MIDI clock and audio clock values almost line up, and the MIDI event elapsed test I showed you before returns true. This is where the second musical note begins to play, but let's see where the previous one ends. It's here. So between the two events there is silence. And finally, the second musical note ends here. So there you have it. Now that you know the theory, you can go ahead and write your own version of this program. We haven't produced any sound yet. We'll do that next time.